You know, deep inside every diesel engine, there's this tiny, almost invisible pause. But that one moment, it controls everything. Its power, its efficiency, and yeah, even that classic diesel sound. Today, we're going to pull back the curtain on that critical pause.
Okay, let's start with a kind of a wild question. How can you make fire with just air? Seriously, no matches, no lighters, and definitely no spark plugs. It sounds like a magic trick, right? But it's actually the core principle behind every single diesel engine out there.
Well, the secret is in this really cool, simple device called a fire piston. I mean, it's one of the most basic ways to make fire, period. And it turns out it's the perfect way to understand what's going on deep inside that engine.
All right, so let's dig into that main idea. Making fire from thin air. Or, to be a little more precise, from air that's been squeezed like crazy.
So it really all boils down to that classic fire triangle you probably learned about in school. You need three things, right? Fuel, oxygen, and heat. Now, in your regular car engine, a spark plug brings the heat. But in a diesel, the heat comes from just squeezing air, a lot. That compression gets the air so incredibly hot that when you finally spray in the fuel, it just bursts into flame all on its own. Pretty amazing. No spark plug necessary.
Okay, so you'd think this whole thing would be instant, right? Squeeze the air, add the fuel, and bang, combustion. But here's the twist, and this is what's so cool. It's not instant. There's a tiny delay, and that's our critical pause. Yeah, inside a real engine, spinning thousands of times a minute, this process isn't immediate at all. There's this tiny but massively important gap in time. It's the moment between when the fuel is first injected and when it actually, catches fire.
And that little gap? It has a name, of course. It's called the ignition delay period. It's exactly what it sounds like, the time that passes from the start of the fuel spray to the actual start of combustion. So, what on earth is happening during that tiny pause?
But before we get into the nitty-gritty, you have to appreciate just how fast we're talking. This delay can be as short as 1,000th of a second. I mean, a blink of an eye is, hundreds of times slower? It's almost nothing. And yet, everything about how that engine runs hangs in the balance of controlling this unbelievably tiny slice of time.
So, let's put that millisecond under the microscope. This isn't just dead air or waiting around. No, it's a super frantic race between physics and chemistry, all happening at once.
You can see here the total delay is actually made up of two parts. First, there's a physical delay, and right after that, a chemical delay. So let's take a look at what's going on in each of these phases.
Okay, first up is the physical delay. This is all about getting the fuel ready to burn. See, you can't just light liquid diesel on fire in this situation. It has to go through a few physical changes, like a rapid prep phase.
So three things have to happen, and they have to happen ridiculously fast. First, the injector blasts the fuel out, atomizing it, basically shattering it into a superfine mist. Then those tiny droplets soak up all that heat from the compressed air and poof, they vaporize, turning from liquid into a gas. And finally, that fuel vapor has to get all mixed up with the hot air to create the perfect explosive mixture. Only then, after all that, is the stage finally set. All right, once that fuel and air are mixed, the chemical delay kicks in. You can think of this as, like, the pre-show for the main event. It's the time it takes for all these little pre-flame chemical reactions to get going. The fuel and oxygen molecules start to dance, things get hotter and hotter, faster and faster, until, boom, they hit the tipping point of self-ignition, and you've got fire. So why do engineers lose sleep over this tiny, tiny delay? Well, because if it goes on for just a little too long, things get loud and violent and really inefficient. In fact, this is where that signature clack, clack, clack of a diesel engine comes from.
And this really shows you what's at stake. When the delay is just right, the fuel ignites nice and smoothly as it's being injected. It's a controlled burn. But if that delay drags on, a whole bunch of fuel gets a chance to pool up in the cylinder. And when that big puddle of fuel finally lights up, it all goes off at once in one massive explosion. And that creates a huge, sudden spike in pressure.
And that right there is the key. That massive pressure spike, that's what you hear as diesel knock. It isn't just a sound, folks. It's the literal sound of an uncontrolled explosion hammering away at the guts of the engine.
And the problems don't stop with just noise. A long delay puts a ton of mechanical stress on the piston, the bearings, everything.
The super high temperatures can also create more nasty pollutants like NOx, and on top of all that, it just makes the engine run rough. So yeah, getting a handle on this delay is absolutely critical.
Okay, so if this delay is so important, how in the world do engineers actually control it? Well, thankfully, they have a few different knobs they can turn, so to speak, to dial in that perfect combustion. Here are some of the main levers they can pull. For example, if you crank up the compression ratio, the air gets hotter, which shortens the delay. Or you can use fuel with a higher cetane number. That's just a fancy way of saying fuel that's easier to ignite. That shortens it too. Pushing the fuel in at a higher pressure, that makes a finer mist, which speeds up that whole physical prep phase. Even just the temperature of the air coming into the engine makes a difference. Every single one of these is a tool to get that perfect, controlled burn.
And of course, modern tech gives us even more amazing control. There are techniques like pilot injection, which are a total game changer. Basically, the engine shoots in a tiny little squirt of fuel early on to get the party started gently. This kind of warms up the room, so when the main blast of fuel arrives, the delay is way shorter. The result? A much smoother and quieter combustion. So, think about that. A pause that lasts just 1/1000th of a second can literally make or break an engine, turning it from smooth and efficient to loud and stressed out. It really makes you wonder, doesn't it? What other tiny, almost invisible variables out there are having a massive impact on the technology we rely on every single day?